This device, of course, is not useful. The whole idea is about cost. I saw this discussion about choosing the target and selecting the filter. What is the mechanism inside it? Why, honestly, do I not know? If I have a target, for example, and I want to perform a breast procedure, what should I do, sir? The sound is gone, doctor. Hello. Hello? Are we listening, sir? I am indeed here and ready to proceed with our discussion and any tasks that need to be addressed. I hear you, sir, in every message. We are all listening. Ha ha ha. We are all listening. I am in a situation with thick breast, Dr. Hani. I can use molybdenum or rhodium molybdenum. Or rhodium molybdenum is fine. Tungsten is preferable only in cases of embolization, but in regular thick breast cases you use the other one. I don't know if there's a problem with the sound, so we are listening. Okay, let's continue. We remember together the topic. I have talked a bit about the issue of contrast. There is also another point in mammography. You want to improve your resolution, not just the contrast. To improve the resolution, you should use both small and large focal spot sizes. You will always find that mammography uses a small focal spot size, and to achieve a small focal spot size, you will find that the anode angle is slightly lower. In mammography, almost small from the key movements. You will find that, in order to achieve this, your anode angles will also be low. When the anode angle is low, you will maximize the anode heel effect that we talked about before, stating that with low anode angles. The photon travels a certain distance. If we assume this is the cathode, it travels a distance within the anode material itself and experiences attenuation. You find that the X-ray beam, or the X-ray beam itself, is not homogeneous in its intensity. You notice that the part close to it does not pass through a significant thickness of the anode material, while the part that does pass through the anode material and is close to the anode is considered low intensity. Therefore, to achieve effective small focal spots, you need a small anode angle. Thus, you will find that the issue here is in the design. The X-ray tube.
We utilize the concept of the anode heel effect and specifically tilt the X-ray tube so that the area near the cathode, which has very high intensity, remains focused on the shift wall of the ADI wrist we are imaging. This way, the part close to the cathode, which is emitting very high intensity, is directed towards the area we are imaging, while the other part, or the area near the anode intensity, is positioned accordingly. Thus, the part here is considered to have higher intensity. Okay, it's as if I am performing a tilting for the X-ray tube to align this part with the schist wall area and make this part low intensity. I will rely on it for imaging the ADI wrist, unlike when I work with it without tilting, which results in an image like this. It will be particularly clear here because I will use it in a way that is clear, especially since I will maximize the anode heel effect here in the mammogram compared to any other technique or imaging modality. The effect will be apparent, giving me inhomogeneity in the resulting image. I need to ensure there is homogeneity. So what I will do is this tilting process. Consequently, I will benefit from the part that is on the anode side. This is the only part I will use for imaging, while the other part will be directed at the schist wall. Thus, I have effectively utilized the anode, ensuring that I do not have inhomogeneity in my beam. The intensity part from the anode will be relatively uniform during this time, providing me with a homogeneous image. In the design of the C-arm, the C shape is evident, and it includes the X-ray tube, a filter, a kilometer, and the ADI brist. There is also a component that can be moved or resized depending on whether I want to use it or not. Additionally, there is a mechanism that compresses to reduce the noise present in the tissues and to separate overlapping structures, which improves contrast and simultaneously reduces scatter radiation. Under the ADI brist, there is a grid that removes scattered radiation, and there is a cassette located under something called automatic exposure control. The radiation scatter is fine, and I have the cassette, which is where I capture the images and receive the radiation, and there is something below called automatic. What is this automatic exposure control? This automatic exposure control, sometimes called a phototimer, functions by detecting the radiation that has already been emitted, and based on that, it starts to stop the examination. For example, you can set it to be pre-adjusted at a certain energy level or a specific number of photons to stop your examination. This is pre-adjusted, based on whether you choose a single breast or a double breast. So it waits for a certain number of photons to provide a good image quality and a certain energy level to give a good image. The automatic exposure control is connected to certain parameters, which are kV and MA. Sometimes it takes something called pre-exposure, which means it takes an image before the actual image to determine the exact amount of attenuation of the breast. It then starts to make automatic adjustments to parameters like kV and MA to provide an image that matches the density of the breast. Therefore, it is called automatic exposure control, which manages the exposure based on the existing ADI brist technology. The problem is that the ADI brist technology is large, so it operates with beam hardening. As we mentioned, if the X-ray beam falls on a large object, what does the large object do? It utilizes the radiation from the surface. The external radiation here will have high energy. So when this energy comes, it will detect that the energy density is high. In this case, it will stop the examination without taking the required exposure. They circumvent this story by using something called an ionization chamber, which is a device used to measure radiation. They use it before and after exposure, meaning it measures what? It measures the ratio between the primary beam that fell and the radiation that was counted and reached the ionization chamber located below. Based on this ratio, it starts to see that it entered as primary and exited as primary. In this case, it calculates the ratio and indicates that significant attenuation has occurred. This is not enough to stop the examination. There are many recipes for the topic that we will address later, but this is a simplified idea of automatic exposure control, which controls the dose that directly reaches the imaging technique I am using. I am here to discuss the use of the anode, whether it's a 0 anode angle or a 16 anode angle. The tilting I did helped me understand that there is a relationship between field coverage and anode angle. When the anode angle increases, it expands the field coverage. However, I need to use a small anode angle, so I don't require a large field coverage in breast imaging. Therefore, what should I do? The tilting you did using a certain angle provided you with very suitable field coverage, as if you had used an anode angle of, for example, 16 degrees. Thus, at that time, you achieved a tilt of 24 degrees with a zero anode angle. So here, if you set your angle to 16 and the tube's tilting to 6 degrees with the same field coverage, you have overcome this problem. That's why this tilting is very important. To give you the same field coverage for the breast, the focal spot sizes used here are 0.3 and 0.1 millimeter focal spot sizes. However, you need to use the magnification technique, which brings the breast closer. This increases the sharpness and enhances the image quality. Therefore, in cases of magnification, you use a smaller focal spot size, which is 0.1, because the difference in sharpness that occurs is treated by using a smaller focal spot size, giving you more resolution in the image. The X-ray tube should operate at low potential, less than 40 kilovolts, and the tube current is limited to 100 to 200 milliampere when I am working with 0.3 millivolts at 40 kilovolts. This is in case I am working on the... Okay, fine. If you are working with the focal spot size, you should operate at a kilovolt of 25 to 50 milliampere, lowering your milliampere to reduce the load or heat load on your anode material here.
Nothing kills. Think about the support side, which is related to the dot, which is a point. And here we are.
Here. The focal spot size will not be reduced. The second law will not be used. A short filament will be used. As we mentioned before, Dr. Hani, I have an X-ray tube with two filaments, one short, approximately 1 centimeter long, and one long, 2 centimeters long. This is a lens. This is a large filament that I can use. Get a large actual focal spot size, which allows you to increase the parameters, and that's fine. In the case where I use the short filament, you reduce the focal spot size, which decreases the actual size, thus reducing the effective size, which increases the resolution. So you decrease the actual size, reduce the effective size, and increase the resolution with me. This means that with the same anode angle, you won't change anything, but you will change the filament size. The filament size will affect the effective focal spot size, increasing the resolution and adjusting the effective part of the magnification. Is that clear? 30, a committee of 30 and 30. Because of the alignment of the tube for field coverage, and for another reason. If I don't do the alignment here, and I take the image of the breast, what do you think? I mean, I can take the image like this. Right. What difference does the alignment make? Why does the angle I changed, or the alignment matter? I will tell you that. Because I am using a very small anode angle. The effect on the anode is significant. What does it mean that the effect on the anode is significant? It means that the X-ray beam coming from the cathode side has a much higher intensity than the intensity on the anode side. This difference is very large here because it increases with the small anode angle. So since it is maximized and enlarged here, I want to address this issue. If I take the image in the loop normally, you will find that this part of the breast exposed to high intensity of radiation, and this part is exposed to low intensity of radiation. Do you think your image will be homogeneous? No. So I need to do some tilting. Why is this tilting necessary? To ensure that the cathode site is directed correctly. You might say, I don't want it to go far from me. I just want the entire breast area to be exposed only to my desired radiation. Here is our doctor. Right now, microcalcification, what does it mean? It means you bring your object closer, right? So, what is it, doctor? Right now, the magnification, what does it mean? It means you bring your object closer to the imaging plate. This is one of the imaging techniques. Or if you want to take a magnification view, you bring the magnification platform closer to the source. So, when we said that I have the focal spot here, and when the object was here, there was no microcalcification. Think about this when we said microcalcification will occur, but its percentage here is low. On the contrary, it will show you a larger image. This is what happens. But the problem, Dr. Islam, is that the number that will occur will be large. Think about the issue of the blurring that will happen at the edges. I want to address this issue. How can I treat it? How can I handle this story? To increase the resolution, I need to increase the factor. That will give me high resolution, so I use a low focal spot size of 0.1 to make my beam more focused and enhance the effect. Increasing the low focal spot size improves my resolution, but the effect on my microcalcification is not clear, right, Dr. Islam? We will make the breast itself adhere to the imaging plate, so there is no moment that is very small. No, there is another arrangement that uses magnification. No, this is an empty space under the imaging plate here. Dr. Islam, it should remain very small. No, there is another view that is taken magnified. You see, this is a distance. This is a video distance. This is the topic. It could be in female doctors. Do all mammograms move and take images, etc.? There is an imaging technique that involves microcalcification. This is relevant. In this case, there will be a distance. Why do they call it the air gap? I agree with you. If we go with okay. But the story is that there is a deputy with Johnny. Honestly, to overcome this problem, I use low focal spot. All right, my dear. All right. Oh. Okay. In cases of microcalcification, it is possible to remove the grid. Why? Because there is a gap between the breast and the imaging plate, and scatter radiation can find a way to move away from the imaging plate. This will reduce the amount of scatter. Okay? Then there is compression. This topic of compression is also one of the important things. Why does it apply compression? For example, if I have microcalcification, as I see here, and they are all stacked on top of each other like this, without compression, you want to spread this microcalcification across your view. So what do? You apply compression, which reduces thickness and minimizes scattered radiation, while at the same time spreading them out like this. When you come to do imaging, you can see them and resolve them better compared to without compression. This is done with a force that you control using specific buttons located under the imaging machine, which press down until it starts to apply pressure on the breast. The force is approximately a maximum of 200 newtons, around 150 to 200 newtons, and you can control it. The compression improves contrast, reduces the scattered radiation present, and also, as the thickness decreases, the absorption of radiation is reduced, which in turn lowers the dose on the breast. For example, in an uncompressed breast, the scatter primary ratio is about 0.8 to 1, while in a compressed breast, the scatter primary ratio decreases to about 0.4 to 0.5. This illustrates the relationship between thickness and scatter primary ratio, showing that as thickness increases, the scatter increases as well, with the scatter from the primary radiation entering the breast and the scatter considered to be coming out of the breast or from the imaging origin. Second, here is the X-ray spectrum, this is the energy, and this is the number of photons, and this is the target molybdenum. If I do not use a molybdenum filter, there is a part that is for low energy. If I am talking about this red curve, it is the part for high energy that has been removed, and there is a part here that has been removed. This is the molybdenum filter, which is considered to be at 20 kilo electron volts. If I use a molybdenum filter, this part has increased, which is the pilot part. I do not know what this color is, which is this part that has increased for me. So you have increased part of the high energy. Therefore, I can use a molybdenum target with molybdenum and molybdenum filter in cases of dense breast, as I was talking about a moment ago. Now, tungsten, which is W, this is the shape of the spectrum. Here, we do not see any radiative shape or characteristic radiation, right? But using the rhodium filter means that there is a part of higher intensity. Unlike silver for you, you can use the material with the filter, or you can also use it with the target, depending on the situation. For me, the filter with the target is the most useful. The whole idea is that the use of the filter is related to the K edge of the filter itself. Here you will find a diagram that illustrates this point, showing the attenuation for each filter available. For example, molybdenum has a K edge of about 20, rhodium is around 23, and silver is slightly higher. So the higher the K edge of the filter you use, the more energy will enter your peel spectrum. This is related to peel thickness and depends on the options available on the machine you choose and the specification of the machine you have. Therefore, when you are buying the machine, you need to pay attention to these points. For instance, if I have a dense breast, what should I choose? For example, what should I choose? What will each filter remove and what will it enhance? This is very important in your selection. Which one will play a role and which one will increase it? This is very important, or it clarifies who has the highest and who has the lowest. The contrast, molybdenum has lower radiation. Of course, the distance between the focus or the distance I use in imaging relative to the film is set at 65 centimeters. I consider this distance appropriate because if I choose a distance further than that, your dose will increase, which is not desirable for the breast. At the same time, if I choose a distance closer than that, it will also affect the part of the distance, and the magnification part is also not desirable as it may give you a blurring effect. So the idea is that you need to choose the right distance, and in some cases, of course, if you are doing something specific. The magnification process is crucial, so you carefully choose your platform, which serves as the magnification standard, and it is meticulously imaged through it in a detailed manner with precision and care, ensuring accuracy and clarity. Here, as I mentioned, the topic is automatic exposure control or automatic exposure sensor. This is essentially an electronic device or detector referred to as a phototimer, which relies on the number of photons it receives or the energy. This generates a signal that controls the parameters of kV and milliampere seconds, which will give me the desired signal-to-noise ratio according to the attenuation that has occurred. If the attenuation is significant, it will start to increase the kV and milliampere to maintain the required signal-to-noise ratio, and this is auto-adjusted by the machine itself. As I said, the system provides pre-exposure to determine and assess the attenuation that has occurred and begins to make pre-adjustments to these parameters. Doctor, can you confirm this? The pre-exposure is what develops the pre-adjustment. Yes, but could you clarify this point? Omra. Okay. I have this here, right? What does it do? This is supposed to be the one who comes to do, for example, IAM, or the one who comes to do the protocol. For example, IAM. If I have a protocol for dense breast or a protocol that I have, usually breast protocols are the same and fixed, meaning the known values are almost constant, because you are using the specific target and the specific filter. So it starts to create these protocols and begins on the machine itself, stating that I want a certain signal to noise ratio, which is the signal to noise ratio